All right. Good morning, everybody. I'm Chenyi from University of Central Arkansas. Like every speaker else, they talk about the background. So I give a little brief on my background. My education is scientific computing or numerical analysis. And then I was in Texas for 12 years, teaching in the University of Houston, and then moved to Arkansas for another 13 years. So what makes me move to Arkansas is they established the department, wanted me to chair the department. So I chaired the department for 11 years. And then what's going on, last 2 years ago, I began to do real job, not do the chair anymore. So can coding, love what I do. So started the project working on the Python, and then I fell in love with Python and tried to make some tools for working on the data analysis. So that's my current interest, what I'm working on. So this project started, realized I started coding last year. I heard a few speakers talk about academia. Yeah, we are not high-paid, we are out of date, we just, now, whatever tower, working our stuff. But I really feel important is how make our education current and then really connect our students with the current development. I feel Python is a great way to do it. So the students in my introduction for computing class, they started with Python, and then I will back tomorrow, final for them. They present their fabulous projects. Just the first semester, one semester course with Python, they create a lot of different useful things. So Python is important. So, but for today's, I try to share with you his outline. So, how many of you actually heard the interval computing? Not many. How many? So that makes my preparation good because I spend a lot of slides on this introduction. So, what is interval computing, and its original motivation, and why it should be, at least I feel, should be very useful for data analytics. That's very useful. Then we talk about some technical stuff on that module, what it includes. So what are intervals and what are the interval vectors and the matrices. So the vectors from the data points, just the attributes, right? And the matrices, just the data table. So then finally, at the end, we talk about the Python module. The module with the current under development is not fully functional as I hope, all right? But we do have something we can do some little demo here to share with you. Hope you will be interested in this. First of all, we're working with data. So we are here PyData. Data is something we want. We look, we try to find the information from it. But currently, data in the computing are mostly stored and processed in point value. We use bytes, and then we record the fields, and then we feel that's what we want, right? In scientific computing, we use floating points, and then the most numerical data we store, we still use follow the IEEE 754 standard in the binary representation. So this cartoon I just downloaded from the IEEE 754 that shows in 32 bits how do we represent a number. The real number we use the 23 bits to record the decimal, the fraction called the mantissa. And then we use the last bit here, positive, negative, to show the sign of the number. And then we have add bits to represent exponents. So the exponent, we use that bias for 127, so we don't have to use a bit to represent the positive negative. So then this charged in here, the number is in the decimal number should be 0.15625. So we feel good. And then, okay, not so good. Why? Our number could be more digits, right? So then, okay, let's use 64 bits, 128 bits, a double precision, quadruple precision. We try to present the number better. So that's the way we get our data stored in our computer. We try to process them. This kind of presentation, do we have a problem with it? Does it matter? Because we are, regardless of how many bits we use to store a number, we have to chop something off, right? You have the 64 bits or whatever bits. So your mantissa, you have to throw something away. Then okay, it's a tiny thing. The representation error, rounding error, it's inevitable. Does it matter? Most of us feel no, it doesn't matter. The little thing, who cares? When we get the gas station, last speaker talked about it in the pump, at the pump. If you notice, always they have some what? Yeah, $2.64 and then 9 above, right? Yeah, nobody looks that kind of 9, but they get what? 1 cent, a penny to the gallon, so they still make the price for their large quantity. For users, we don't care. So, but can we really don't care that? So here is a simple question. We do have a sequence. First number is 1. The second one is 1/3. We recursively evaluate it, and then the question simply is when n approaches infinity, what would be the xn? For the recursive sequence, for all of us, a piece of cake, let's get into Python. So we define the sequence, and then x0 is 1, x1 is 1/3, then for k in range 2 to n, we don't want to print too much. So with 100 of them, we modulus 10, and then we print them out. Every 10, we print them out. All right, we call the function sequence, and we get the output. So here's the output. So x10 would be something to 10 to negative 5th power, 20, negative 6th power, 30 would be to 3.99, and 40, okay, yeah, and 50, 60, 70, boy, and then we can see every 10 we move, and the exponents raise to 10 to the 6th power. So 18, 24, 30, 36, 42, right? In the trend, with the number would be grow bigger and bigger. So what the Python tells us, and I could try to run more, we change the parameter, we ran to 550, become another number. So just, our computer said, I can store it, I don't know what's going on, right? That either way through none, we fix the problem. Okay, so for us, the data analyst, we feel, yeah, we work on it, look at the program, we trust the answer, right? So let's wait a minute. Mathematically, by the induction, you can prove that the sequence actually equivalent to 1 over 3 to nth power. As n approaches infinity, this sequence certainly goes to 0. But what we had a moment ago, it shows you keep increasing, we will get infinity, right? Whatever language you use, whatever computer you run, as long as you use the floating point arithmetic, you will get the sequence. Sometimes it goes to positive infinity, sometimes it goes to negative infinity, depends the environment you use. One reviewer referee reviewed my paper many years ago. He said, oh, if you use IEEE 754, you won't have the problem. I said, boy, with full respect, that's incorrect. You know, now we're running IEEE 754. So what is the difference? So that is certainly a big problem, right? Okay, a data analyst will analyze the data, Then we tell you, okay, so according to my calculation, you should flow now, all right? The elephant get everything, but looks like he's not ready to jump in the ocean or something, or the pool, right? Are we getting our computational results correct? Can others trust our analysis? Will we get something like the elephant? According to my calculation, you should flow, but yeah, it doesn't matter, elephant can swim, right? I think, yeah, so that's okay. But how about something else? So the idea for interval computing was developed initially by Professor Raymond Moore. I also dedicated this speech to him as well. I met him, I worked with him, and he passed away earlier this month. Right? He created the idea when he was a grad student in Stanford for his PhD. He tried to figure that problem, the whole computer does not give us a reliable solution at the time. So he proposed the idea called interval computing. If you track the history, they may have something else, talk about it, but we said the modern interval computing, the idea really started to become a branch of computing is from him, yeah. His fundamental theorem of interval arithmetic is, so whatever function you evaluate, so what's going on, if you put these parameters or arguments as intervals, then the result should contain all the solution in it. So that is the fundamental theorem. And his dissertation actually is called automatic error analysis in digital computation. So that time he actually worked at Lockheed, not Lockheed Martin, that time Lockheed. That time was also the Vietnam War and the Pentagon, they want to see all the missiles, whatever, so why not hit the target? So that's, the computer that's wrong or something, whatever reason. So he tried to analyze his job is how we analyze error automatically. Why don't we have to worry about it? Do this in the numerical analysis field. You always try to figure out is your algorithm stable? Is kind of little perturbation at the beginning? Would that impact final results like this ugly sequence we used a moment ago, right? Yeah. Would that little error cause 0 go to infinity? What a huge difference. So the basic idea is we cannot represent a floating point precisely, but we could use 2 points and bound it, make it an interval. For example, we all know pi is infinite non-cyclic decimal. It's an irrational number. So no way to represent the pi precisely inside a computer. So how we do it, let's use the lower bound and upper bound both. We know pi must in between. And then what do? We use these intervals in our calculation based on his fundamental theorem of interval computation. Then we would get what? The final result would be in it. Yeah, we don't know what's going on, but with a basket, we use the basket to the operation, our data, and then we will get the correct answer. No, but not precisely. We know the answer must be within in our basket, right? We carry out. If this basket is too big, probably we need to do more work to ensure, to narrow the range, we know what would be useful. So here is a few examples on the interval computational arithmetic. Do the addition is easy. So 1, 2 plus 2, 3 would be 3, 5. The lower bound at the lower bound is 3, upper bound at the upper bound is 5, so we're done. But however, when we use the 3, 5, we subtract the 1 operand, we will not get 2, 3 anymore. Because do a subtraction, your lower bound would be what? 3 minus 2 is 1. Minimum here, maximum over there. So anything in here could happen to subtraction to the other side. So we take the lower bound, upper bound for reliable computing. That here is 1/4. So that is okay. The addition, the inverse of not subtraction anymore, interval subtraction anymore. And then we do multiplication, and you will see you do the division. Same thing. So that is some kind of fundamental thing in interval computing people have to deal with. All right. Does interval computing work? Of course. Otherwise, I won't work for it for over 27 years, right? So here are some really awarding, winning applications. The Computing in Chemical Engineering Award of the American Institute of Chemical Engineering, 1998, to Professor Mark Stazzer. And here's my colleague, his grad student worked on this project with him. And then in 1990s. So what he found is using the interval methods and try to solving some chemical engineering designing problem and find some solutions for nonlinear system never found before. But with interval computing, they found it. So that's the only award they give to him in the chemical engineering, Computing in Chemical Engineering Award. The other one is the David Robbins Prize of American Mathematical Society. The 2007 award goes to Samuel Ferguson and Thomas Hall. It's a proof of Kepler conjunction. So that conjunction over 300 years old, and then Samuel Ferguson did it, and then with his that time PhD advisor, I believe it's the University of Michigan. By the way, Mark Stazzer, when he did this award, he was in University of Illinois, Urbana-Champaign. And then he moved to Indiana. Yeah, now he works in Indiana. They have some other things. So I want to bring this up to say, okay, interval computing really works. Yeah, you can produce a result-winning results. Okay. Yes. How about the example you used a moment ago? That with interval computing, we work on it. We get, okay, x0 is 1, is the interval. And x1 is that use the bound with the interval to bound it. And we do the loop again. We found, okay, it does not give you something. However, it gives us something. If you look at the lower bound is what? Negative sign, even though the exponent goes real high, that the high bound goes what? Positive. So what does that mean? That means the true answer should reside in this interval. Although at the very beginning, that's not much, both positive. By the way, we'll show you a moment later what's going on here, right? Yeah. So, all right. The whole idea, the original idea is what? The use intervals to bound our operands, bound our data. We try to figure out what the final result would be, right? Yeah, we know our answer is within some range we expect. Okay, so that branch called what? Called reliable computing. We reliably tell you what the computing results should be, the range should be. Now we switch our attention now. So okay, that's the original idea. So how it used, what it used for data analysis. In data analysis, I guess what we want probably is the exact science. We try to find something possible. You give us data, we find the knowledge. Do we have 100% of like the proof the theory that the answer is perfect, it's correct, no problem? Probably not. We use statistics, probability, we means what? Looks like this, but possible. So our science, the bottom line, I feel the probably is an inexact science. We find a computational result, but it must be verified by the real world. Or once it's correct, might not be always, right? Yeah, so we have to find it. So the life cycle for data analysis, my feeling probably can start from anywhere here. Okay, so let's say we start from data. That's most are focused. Big data, whatever data, we start with data. And then we crunch the data, we process it, whatever way we use, right? We try to find some knowledge or information that what we hope. That is correct. Hopefully, but we don't know. Let's use in application, apply our knowledge in application. And then we observe the result. If it's correct, okay, so we got data, we can use it. We're not right, yeah, from data we try to figure out what's wrong. So that cycle never ends. In this data analysis cycle, so what do we assume our assumption? If in unsupervised training, we assume what? We do not have any knowledge but data. So what we try to find, objectives, okay, from the data, we try to extract possible but not perfect information. We hope it's perfect better, right? Yeah, we hope, but most likely, we may not be able to guarantee our answer is perfectly correct. So we got the imprecise rather than rigorous mathematical theory to working our data. We do have theory, right? Yeah, but this theory itself, like the regression analysis, do we guarantee the regression then give us the function? But mathematically, it does not guarantee any observation will be resized in your regression, even you with 95, 99% confidence, even 99.99, right? So the interval computing, so what do? We feel for data analysis, yeah, it's not a different objective from the reliable computing. It's not trying to find something perfect, but to find something working, right? Get the information we want. So we don't have to follow that fundamental theorem of interval computation. So in the interval computing community, people feel more like my own feeling, a little bit religious to the theorem. So, okay, we have to guarantee everything is correct. But if your data itself is incorrect, you're imprecise, the knowledge, the output, you not expect perfect, it might not be necessarily follow the theorem. So what do we look at it? Do we look at the interval, the new data type, instead of point-divided data? So why interval data good? Because interval data includes uncertainty. You are not make the data the point on a single point. You get what? Some variation included in your consideration. And in real world, when we observe data, our observation most time are what? Are interval ranged. They are not what precise a point. Why should we record them as a point? Why don't we record them as intervals? And the more importantly, the use interval computing, many results are happening with in knowledge processing, in data analysis. I'll show you an example. And also, for big data, it has a potential. Why? Big data is so big because we look at them as every different points. If we use a small interval to cover a region to represent that one, we are not distinguish them as singular different points. We look at their entire property. So interval computing, yeah, they should have some role to play in data analytics. So two grad students work with me on this data analysis, cluster analysis. They get some good results. Yeah. One is published 2 years ago, 2 or 3 years ago. The other one is going to publish today. Not today, this year. Yeah, I expect. We do some of the interval-weighted matrix games, the decision-making system, interval-weighted graphs, and the flow networks, and the time series interval least square analysis, or the regression. So here we show the example. This real-world data is from economics. We try to analyze the data with the S&P 500. So I'm not an economist. I don't know it. When I buy stocks, I always get something really crazy, right? Yeah. So I don't want to try to do that. But one of my colleagues collaborated also in my school. He is computational finance professor. And then when we talk together, I said, okay, I say your stock markets, you have the opening price, closing price, you have the day low, day high. There should be intervals, you know. The point to do it probably not work. And then his work interesting, one of them is to predict the big economy's trend. So he got data from S&P over 100 years and collect. We started the project in 2005. So that is the traditional way to do it is the point. So they get the prediction and answer, here the years. So yeah, hard to see. We'll see next page. And what they do is, okay, use the point prediction, they add or subtract the percentage of standard deviation and then with the error. So what's going on? So here's the true annual variation for the S&P 500 is in this. The yellow and pink. Yeah, so in here. But with the higher confidence, probabilistic confidence, I believe 95%. So from the previous, the point solution, so we got the prediction, traditional way, predict lower bound and upper bound. So what's going on? We can see, yeah, with the 95% confidence, probabilistic confidence, we found what? We found from 1940 to 2003, that actually 2004 should be at the end, yeah. We found that one, yeah, it's big. Really, you have it, but far away from real. And also, even we can see here is a completely missing, 5 completely missing. All right, you want 70 years, but you get what? Not many of them just completely missing. So how that 95% confidence? Not much less than 95%, right? Okay. Now I use the interval computing, crunch the same data. So here is what we got for him. Let's publish several finance journals. All right, yeah. So what we got is, okay, the interval computing shows, yeah, here's the lower bound actual, the yellow still, the predicted one. and that the above two, so this is the actual, this is our prediction. Much better. Pay attention, please, here. Yeah, what do we do here? The range here is about the less than 20%, 17. Here is the negative 0.15, 15%, and then a little bit lower, yeah. Let's look at the previous one, the traditional method shows what's going on. We have 0.15 here, they have what? 150 or something, here it's below is what? Way far apart, way apart from the real. So that means the interval computing actually truly makes sense. It produced real good result with real data, and it works. Okay, so that finished the introduction part, and then I know we have lunch in a few minutes, right? Yeah, so I promise you, yeah.
You have 9 more minutes.
Oh, 9 more minutes? Yep. Okay, I'll promise we'll finish before lunch. Don't let you hungry, all right? So here's a summary of that example. It's the classical or traditional ordinary least square. The mean error is the normalized percent, 20%, and then standard deviation is about 19%. And if we use the confidence interval, what we got? Yeah, we got something even higher error. Yeah, 72%. And then we have a accuracy ratio related to the Jaccard measure, the index, to show how precise the answer you got, the accuracy. So this is the interval least square. What we use the mean and the max to use that lower bound, upper bound of the interval. So we got our mean error only 5% compared to what we had before. And if with the 92% confidence interval, that's the 1.5 deviation. So we get only also 5%, we get a real high what? The stability. Our standard deviation is low, right? If the standard deviation is low, means what? On the bell curve, it's really slim, right? It's good, okay? So it's very good. So we get the better answer in terms of what? High accuracy, higher stability. And we do not missing anything. All right? So, yeah, the summary on that part. Now we switch back to the interval computing. Okay, it's good. Whatever you say as a salesman, you shall sell interval computing, right? What you got here. Now, what is for me? So how does it work? So we move to the interval itself. Yeah. Intervals, we do have kind of what's called a mathematical interval, so the real numbers. We have machine interval because you put the computer represent it, must be machine representable. And then we have an empty interval, so it's nothing because interval have the dual property. What the dual property means, on one side is what? It's a number. Operand. You can do addition, subtraction to arithmetic like everything else in the points. But on the other side, interval is a set. You can use a set operations, union, intersection. You can find all of these things. So, yeah, if the empty set makes some sense in knowledge, right? Yeah, so notation-wise, we use the boldface, the letter for interval quantity, lower underscore ups overline as the lower bound, upper bound. So it has a midpoint, you have this radius, you have its width, the representation, you could use the lower upper bound represented, you could use the midpoint radius represented. And the operations, you can put it in the properties. Yeah, here's some operations. And the arithmetic operations we mentioned, and we also have additive inverse specified. And the set operations and some other operations, the comparison operators or intervals. Then we have the interval as arguments for fundamental functions, like what, sine, cosine, polynomial, or or transcendental functions, all implemented. Okay, and then okay, I will skip a slide. Just we'll get it back here a moment later. I only have a few minutes. Yeah. The interval vectors, so we scale single interval to make them into list. And then here's the operations involved. Here's the definition. The matrices, we use each entry of the matrix is an interval valued. And then we can do the operation like this. Yes, all right. Okay. The interval software available in different languages, C++, Fortran, Java, MATLAB, Maple, and also the IEEE 1788 interval computation standard is expected to approved in June this year. So we voted already with our group, worked for years, and then the formal document is through the bullet vote. Second circulation also is done, so it's, it will be a standard release expected in the last meeting in June. Still expect that, all right? We never know that until it officially published. But if it's not published, officially released by IEEE, I would be surprised. But still unreliable, who knows, until the time we know what's going on. So that's a new standard. Okay, so I probably have 2 more minutes.
Yeah, just allow time if you can for some questions.
Yes, I will do that one, yeah. So the standardization is on the interval computing itself for the IEEE 1788, going to be released soon. And the other one, interval blocks. That's a project I worked with Jack Dangara years ago, and then included in the module I'm working on. So I also want to acknowledge the grant I received from National Science Foundation, public money, your tax, right? So used always, whenever you talk, you have to. I also want to thank you guys, and thanks to National Science Foundation. The current status for this module is still under development, not fully, but I will show you the demo. And most of the things I've showed you on the interval and the vector and the matrices are implemented already. So here, demo version. So I try to show a demo. Yeah. Yeah, I'll just use that. Come on. Yeah. Here's the interval. So that's a class. So you have 3 classes implemented. So let me just run this module, the testing. Yeah, we run this module testing. So it just really doesn't, on the time limit, to show that we just test everything. So the interval, all 3 classes we tested. And then what I'm trying to do now is the, oh, come on here, yeah. We can also see the documentation of it, yeah. So you can see the module docs. Come up, yeah. So that's, the shows what's the classes involved and then how that works, all right? Now last, I try to run that example. Yeah, let's try that example. Then I'll try to make something meaningful. So I call it the sequence. This sequence we implemented in different version of functions. That's the way we did at the beginning, use the traditional way. So this way we did use the interval, but naive interval way. But here is the use the follows the Moore's theorem. What we do, what we got is let's run this. Yeah, why the F5 easily? If it's a naive way to run it, you get both ends, -1 become negative infinity. You mentioned a moment ago. Positive negative infinity, negative infinity. All right? But in here, it's the reliable interval arithmetic. We do it, you see what we got. We got the answer. Let's move down a little bit. Yeah, so we know we found it. All right. All right. Yeah, thanks for your time and.
We have time for like one or two questions. Yes, question.